Hello everyone. Welcome to Ebasiq video tutorials, your go-to place for mastering AI, Python, and computer science concepts. My name is Chandragirish, and in today's video, we are diving into a simple and yet powerful algorithm, which is nothing but binary search. So why binary search? So it's a fundamental divide and conquer algorithm that makes searching incredibly fast. Okay, and we will break it down visually and I'll implement it step by step in Python. So what's in this video? We will discuss on understanding the concept and the need for the binary search, time complexity analysis, why order of log n is efficient, and recursive as iterative approach, when to use what. I'll give you an example walkthrough, finding an element in a sorted array and the code implementation, writing the binary search in Python. Okay, so let's get started. Stay tuned till the end. Don't forget to like, subscribe, and hit the bell icon for more in-depth tutorials from Ebasiq. So before checking the difference between order of n and order of log of n, we will start with why binary search. So in this, as I told you, imagine you, let's say, you have a phone book with 1,000 pages and you need to find a name. So with linear search, you could check page by page, which is worst case, which in the worst case, it will take around 100,000 comparisons. Okay, so with binary search, you open the middle. If the name comes after the middle, discard the left off. Otherwise, discard the right off. Okay, in just 10 steps, you can find the name. So that's the power of binary search. So binary search works efficiently for sorted data, let's say in search engines, databases, and AI search optimizations. Okay. And for example, if you take a linear search, searching for, let's say 42, number 42 in the set, in the list, let's say 10, 20, 30, 40, 42, 50, 60. So it takes 5 comparisons. So same if you take for a linear search, finding 42 maybe in 3 comparisons by halving the search space. It will work like that. And if you see the time complexity analysis, so order of log of n. Uh, Now let's talk about why binary search is so efficient. So with linear search, for n elements, the worst case takes n steps, that is order of n. Whereas in with binary search, every step of the search space means log of uh, n steps. That is nothing but a order of log of n. Okay. So for example, here we have taken n equal to 16. So at most log 16 to the base 2 is 4 steps. Okay, if it is, let's say, 10 lakhs. So at most it is nearly 20 steps. Okay. So, so that is why binary search is widely used in large scale applications like search engines, stock market predictions, and AI recommendations. Okay. And then, so binary search can be implemented in 2 ways. As I said, iterative approach using loops and recursive approach using function calls. So both have order of login complexity, but recursion uses some extra memory because each function call adds to the call stack. So let us consider, for example, searching for a number 50 in the list of values like 10, 20, 30, 40, 50, 60, 70. Iterate approach keeps adjusting left and right using a while loop. And recursive approach calls itself with a smaller range each time. Okay, so while regression looks elegant, but it's not memory efficient for very large sets, data sets. Okay, and I have given here next slide. So walkthrough. So let's now talk walk through actual example of a binary search. So if you see here, the array list is 10, 20, 30, 40, 50, 60, 70. So target value is 50. So I want to find the value 50. So here first it will go with the middle element. So that is nothing but 40. So it will compare 50 is greater than 40 and search within 50, 60, 70. And then second step 60, uh, 50 is less than 60 and then search for 50. And finally, uh, middle element will be 50 and element found at index will be 4. So binary search finds the element in just 3 steps instead of 7, which is in case of linear search. Okay. And we will implement the code in Python. We'll see that. Now, here, if you see, now we'll discuss about the step-by-step implementation of a like iterative binary search using loop. So here, first, if you see, uh, definition, binary search iterative. So which is a function definition. First, we are writing the function definition and we have to pass 2 arguments. So ARR and target. So ARR is nothing but it's a sorted list when we search for a target that we have to pass. And then we have a target, the element we need to find. And step 2, we we are actually initializing the variables. So here left equal to 0, it represents the starting index of the search space. And right equals to length of array of -1, which represents the ending index of the search space. So this means we are searching the entire array initially. Now we are looping until search space is valid. Okay, so where left is less than or equal to right. So the loop continues as long as left is less than or equal to right. Now if left is greater than right, it means that the search space is exhausted and the element is not found. Okay. Now what we are doing, we are finding the middle element. So here it calculates the middle index of the current search space, and instead of uh, here we are using uh, instead of mid equal to left plus right by 2, we use mid equal to left plus right minus left uh, floor division by 2. Okay, so to prevent integer overflow in very large arrays. So now floor division by 2 ensures that we get an integer value. Okay. So now we check. Now we are checking if middle element is the target. So if array of middle element equals target, we are returning the element that is middle element that is found. So and if the middle element is equal to target, we return the index mid MID. And this means that array element is found in the array. And then we are deciding the next space search space. Case one, like if target is greater than the uh, middle element, Okay, so here we are searching the right of. Okay, so if array of mid is less than target, the target must be in the right of. So we'll eliminate the left of by updating left equal to mid plus 1. Okay, and the case 2, if the target is smaller than the middle element, then right equal to mid minus 1, which is we are searching left of. Okay, so if array of mid is greater than target, the target must be in the left of. So we eliminate the right of by updating right equal to mid minus 1. Now last one, if the element is not found, element not found case, so if the loop exists, left is greater than right, it means the target is not in the array. Okay, so we return -1 to indicate that the search was unsuccessful. Okay, so now we have defined the binary search iterative function. Now we are taking the example, let's say array 10, 20, 30, 40, 50, 60, 70. We have taken, and the target what we want to find element is 50. So whenever you search based on this criteria function, we are passing the array as well as target value here in this function, and we are printing. If it is returning -1, means element not found. So our value 50 is found at index 4. Okay. So here, like there are 3 iterations here. It will take in 3 iterations. Okay. So this is about the by iterative binary search. I hope you guys understood. Uh, Now we will see recursive uh, uh, recursive binary search. Okay, so it is here. So in this, we will actually find the middle element of the array, and if the middle element is equal to the target, returns its index. If the target is smaller than the middle element, repeat the search on the left half. If the target is larger than the middle element, repeat the search on the right half. The process continues recursively until the element is found or the search space is exhausted. So here first we are creating a function binary search recursive which takes 4 parameters. Array, the sorted array, left the leftmost index of the current search range, right the rightmost index of the current search range, and the target is the value we are searching for. Okay, and then stop condition. So if left is greater than right, okay, and we will return -1. So if the left index exceeds the right index, it means that the element is not in the array. So we return -1. And finding the mid index, so mid equal to left plus right -1 floor division 2. So we calculate the middle index to avoid the overflow here, and we are using the floor division here. And now next, if we are checking if mid element target matches the target. So if array of mid equals to target, return mid element. If the middle element is the target, then return its index. And the recursive call happens here. If the target is greater than the array of mid element, then we are writing here, we eliminate the left off and search only the right off, that is mid plus 1 to right. Okay, so search the right off. Similarly, in earlier cases, if the target is greater than the array of mid. This case is if the target is smaller than the array of mid element. Okay, so we eliminate the right off and search only in the left to mid -1. Now what we took, array same thing, the target is 50. So by the search, we are doing and passing the values. Okay, so its left is 0 initially. The index, the 10, an array 10 to 70, and right is the last index, which is 6, and target is 50. So that's what we passed here. Okay, and then we run this, call this function, and then if it is correct, then it will found it fourth. But the internal complexities, it is a recursive, so that is different from the iterative binary search. Okay, the time complexity, we can say best case, if best case as order of one if the middle element is the target. Worst case, order of log of n, since we reduce the search space by half in each step. Okay, space complexity, order of log of n due to recursive call stack. So the conclusion is the function efficiently searches for element in the sorted array using recursion, but the base case ensures termination. The midpoint calculation prevents the overflow. The recursive calls reduce the problem size in each step, and the algorithm runs in logarithmic time, making it easier, much faster than the linear search. Okay, so that's the thing. So I think you guys enjoyed the recursive binary search and the iterative binary search. Thank you. See you in the next video.